This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon, everyone. So today, so basically in 3 sessions, I'll talk about polymers, fibers, and metals. These are mainly the focuses of stuff that you can put into the body. So it will be 3 lectures. Today's one is about polymers, and that's the chapters of the book that is more relevant to this part. I think in coming slides probably there's more like page numbers exactly, so that you don't have to read the entire chapter if it's too long for you. Okay, so we'll start. My name is Fatima, as you saw in the first session. I'm working with Peter Lee. I'm also working on more like mechanical testing of tissue like cartilage and bone and stuff. So we're doing a lot of finite element at the moment. I'm working, the focus is more like in the properties of the equine, like race horses, the bone of race horses. There's a lot of injuries in there. So if any of you is interested in doing any sort of research, so last year we had students that did some sort of voluntary research assistant type work with us, and then they continued to convert that into their capstone project. So if you're interested in doing something like that, we do a lot of finite element, a lot of imaging, with that focus. So if you're interested, just let me know. We can talk about that. Okay, so about polymers, a little bit of history. They've been around, it seems a lot about 60 years only. So the first appearance was around 1960s, where surgeons started just putting different materials like implants and stuff into the body. So the purpose at the time was obviously sort of survival and trying different materials. And as you can imagine, it was very early days, so there weren't any regulations, so you can imagine there could be a lot of complications like infections, or they didn't really know how it's going to go, so it was a very early start. But then in about 1970s, it was the time that interdisciplinary research started. So what happened was that probably surgeons realized that maybe if there are more scientists or engineering people who know more about materials rather than necessarily human body, if they merge together, they come together, they can probably be more successful. So that's when it started to bring physicians, scientists, and engineers into the picture. And then about 20 years later, the development of composites started. So this is more about polymers, so they could sort of, they weren't limited to whatever just is in nature. They could do more engineered stuff and play around with the materials that are available. So sort of plastic, as in what we talk about is the advanced form is polymers with all sorts of materials that could make for different uses. And then only in 2000, around that area, the concept of tissue engineering came into the picture. So this was a very new emerging thing at the time, where now it's not only about dead materials, they're taking live materials, as in cells and stuff, and then use that to engineer a tissue, a live tissue. So that was really something very different and interesting. And all the way that so far you can see that how it's been really evolved so far. So in this entire biomaterials, I guess you're getting very familiar with all the concepts of what's available, and hopefully you will have good ideas in your own projects as well. So yeah, this is a little bit of history as in where it started, and we're going to study where we are today. So as I said, today we talk about just polymers, and then I think next Friday we'll talk about biotextiles, I guess. And then next Tuesday we'll talk about metals. So this is the page numbers that you will have in the lectures, so you're going to read about it. A little bit of introduction again. So polymers are probably the largest class of biomaterials. And because they are like synthetic and polymers, you can play around with the structure of the molecules and the mers, if you like, so single mers, and then you can play around with to create a lot of different polymers with very different type of material properties. So they're becoming the largest class of biomaterials, and they can be used in all sorts of applications like orthopedics, dental applications, soft tissue and cardiovascular implants, all sorts of things. What we classify the other type is if they're natural or synthetic. So if they're natural, we've got them from plants or animals, so they're like, we haven't done much to them. They're whatever exists in the nature. For instance, natural rubber, cellulose, or sodium alginate, which is from a seaweed. So these are whatever available in nature. Animal-based are tissue-based heart valves, sutures, and collagen is a very common type of polymer that exists in nature. Synthetic ones are what have been made from in industry from different molecules that are available. So they again, depending on their sorts of behavior, can be classified into hydrophobic. These are like PETs and PMMA and stuff like that. So they are not dissolving in water. So that's, for instance, one of the properties of these materials. Or they can be more polar, like nylons. So these are the behaviors based on their molecular structure. So if they are attracted to water or not. Basically, they have a phobia of water. That's what hydrophobic means. Or not. They can be easily dissolved in water. So these different properties. Or they can get swallowed in water swelling. That's another property. So this is just giving you an idea of range of properties that they can have. But for you, as a biomaterial, what you would like to do, biomaterial engineer, what you would like to do is to know as much as you can about these materials, so what sort of properties they can have potentially. And then you decide based on the application that you're going to think of. So is it like for a rubbery material that you need? Do you need it for heart valve? And for a heart valve, for instance, what sort of properties are you looking for? Are you looking for a strong material? Are you looking for an extendable material? Are you looking for a material that is dissolving that can be dissolved in water? All sorts of stuff. So you need to know about the application, what's needed, and then what's available in there. And then you decide what can be used, basically. It's sort of like a material selection. And of course, if you're a chemical engineer, you need to know how they are synthesized, processed, basically how they're made. So these are the ideas that we would like to discuss a little bit today. Any questions so far? So all of you did remind what project you're going to have, right? Because I remember people said early on. And I can imagine probably most of you have some sort of polymers in the structure of the materials that you're going to design something, right? Or metal, or how many of you have polymers in there? That sort of material, or you haven't chosen the material yet? No idea? So for instance, if you're going for an implant, like a hip implant, you remember the jaw implant that Peter showed you the very first session? There were two components, definitely. So there was an implant part, there was a polymer part where you need a soft and a stiff material for the joint. So that was the polymer type. And then you have a very strong part, which is like made from metal, titanium, that you need to connect these two parts. So yeah, most of the time, if you need a very soft joint surface, basically, so you need contact of the joints. You need very stiff material, but you need to be very soft as well, so it's not wearing much. And in those cases, most of the time, you will go for a polymer. Okay, so that's another example I just wanted to remind you of. These are more, so like, as I said, hard contact lenses, for instance, that's another example. Bone cements, denture-based, they're most of the time made of PMMA, methyl methacrylate. Or you can have very high molecular weight, that we'll talk in the coming slides what it is. That's more used for bearing surfaces in artificial joint. That's what I'm referring to. So it's like a joint, it's like a bearing, so you don't want any friction or any hard contact surfaces in it. It has to be actually hard, but you don't want any friction in it. Or PET, it can be used in artificial arteries. So here you probably need more extensible materials, more flexibility, because it's an artery, obviously, right? So you don't want anything stiff. Or in catheters, what's usually used is polyurethanes. The other examples is like polyhema. This is used again for wound dressing, soft contact lenses. Silicones are used for breast implants. I don't know if you have done the cases study on that one, or it's your second one probably coming soon. The other one is polypropylene, which is very much used as sutures, heart valves, and finger joints. And biodegradable sutures, which is like polyglycolide. So these are all sorts of polymers that you can have. Collagen, again, artificial ligaments. So this has been used extensively for this application. Fibrin glue, coral, which is used for microporous bone substitute. So if you have a trabecular bone, which is like inside the, like right beneath the joint most of the time, it's very trabecular structure. So it's exactly, if you look at it, it's exactly like a coral material. So there's a lot of pores and stuff in there. And it's stiff at the same time, so this is a very good substitute for that. And cross-leg pericardium, that's again for artificial heart valves. So before I go into some explanation about the molecular weight and other properties, maybe I can show you some example of polymers, for instance. This is a very nice one about contact lenses. Okay, how do we... I think it's connected to the...
Contact lenses correct faulty vision without anyone knowing the wearer even has them on.
Properly?
What goes into making these tiny optical aids is really eye-catching.
I don't think it's connected to the...
Contact lenses have been in existence for over a century. At first, completely rigid, they have become gas permeable and as flexible as gelatin. These small polyhema discs are used to make soft polymer contact lenses in a variety of colors. We see here a patient's prescription, essential to the fabrication of lenses. The process begins with the data processing control of the shaping. Data is supplied by a computer, which controls a digital lathe. They begin by shaping the inner curvature of the lens. This digital lathe, rotating at 6,000 revolutions per minute, is equipped with an industrial diamond. It shapes the inner surface, the part that touches the cornea. It must be free from any abrasions and imperfections, and is polished with a superfine abrasive paste. Polishing is a crucial step because it assures excellent comfort and perfect vision. A technician measures lens thickness with an extremely precise gauge. They now shape the outer surface, the part that touches the eyelid. The lens is glued with a special warm wax. When the lens is completed, an ultrasound device will remove the wax. The wax takes on the desired shape in just seconds. The comfort of a lens is also determined by its thickness. It must be as thin as possible while retaining sufficient solidity. They begin by shaping the outer diameter of the lens, which takes only a few seconds. They now polish the outer surface of the lens. This polishing, done at high speed, calls for an abrasive paste, some oil, and a small polyester cotton ball. This apparatus polishes several lenses at the same time, a step that takes only 60 seconds. With everything computerized, quality is incomparable. A technician then polishes the rims of the lens. The polymer is hydrated to make it flexible. Lenses remain immersed in a balanced pH saline solution for 24 hours. The lens becomes engorged with liquid and expands, reaching the desired proportions. This optical topographer is used to verify through color distribution whether the spread of optical power in the lens is precise enough to assure perfect vision. And now we proceed with another important testing procedure. The soft, fragile lenses are always handled with the greatest of care. This unit, called a frontofocometer, is a metering device which verifies the optical precision of the lens. The lenses are now completed and are cleaned. They're stored in containers filled with a salt solution. This little vial that we might find at optometrists is sealed with a silicon cap and another of aluminum. These vials are placed in a sterilizer at temperatures of 250 degrees Fahrenheit for an hour and a half. The contents will remain sterile for up to 7 years if not opened. The production of a lens involves 14 steps. If we exclude the rather lengthy hydration process, actual lens production requires only 15 minutes. They can produce almost 1,000 contact lenses per day, all made from these tiny colored discs.
Cooler. Do you want to see another one, or? This is wound dressings. Maybe I'll show you this as well.
Now, suturing is generic to all forms of surgery, but I'd like to just talk about one specific application of sutures to cardiac surgery, and that is for the anchoring of devices into the heart. The commonest device we anchor into the heart is, of course, the artificial heart valve. And it doesn't matter whether it's a mechanical valve, such as this one, made of pyrolytic carbon and metal alloys, or whether it's a biological valve, such as this one, a pig's aortic valve. They're all mounted on frames, and they have a sewing ring of a material such as Dacron. The surgeon places sutures through the heart at the point where the diseased valve has been removed, and each of these sutures is passed through the sewing ring, and typically we would use perhaps 15 double-ended sutures to sew in the valve, and each suture is tied 6 times, so this represents quite a considerable time, and it's a tedious procedure. There's still a lot of work we can do with materials of heart valves. There are problems with the existing valves and materials. For example, the mechanical valves made of pyrolytic carbon and various metal alloys are prone to thrombosis, and this requires patients to take anticoagulants each day. The biological valves are prone to calcification and degeneration, and they can't be used satisfactorily in children.
Okay. So, yeah, you see how important it is that we know what sort of mechanical properties these materials have, or all sorts of other properties. For instance, these sutures, you probably would like them to dissolve after a while, so you don't have to do another surgery to remove the sutures themselves. So after they've done their job, they can be biodegradable, just disappear from the body. So the first thing we can learn about the structure of these polymers is the molecular weight. Obviously, like any other material. So this is more sort of, if you think of a metal or just a normal simple material, you can think of their density sometimes. So here we have two concepts of molecular weight. The first one is the first moment of the molecular weight. So this is just an average. So if you have, if you think of a polymer as in, so basically, if you think of polymers, it's like from the name, you have mer, which is like single molecule or singular structure of the material, and then you have poly. So you can have a specific molecule or a specific combination of molecules, but then you can shape them differently into different structures of polymers, right? So when we're talking about the molecular weight, you can have very uniform type of molecules into that structure of polymer, and then when you are averaging, you will have one number for that. But then again, you can have very similar molecules, but then combined with bigger combination of molecules or bigger weights, right? So you can have covalent bonds and everything, but then you can have the same weight. So your first Mn, I think, right? Which is the first Mn. The first moment of inertia is going to give you just an average. So it can be similar for these two types, whereas your second moment of molecular weight is going to give you more information as well, as in how uniformly these weights are distributed, right? So if you have a very uniform structure, the PI, which is what we call it polydispersity index, and equals to second moment of molecular weight divided by the first moment. If you have this as 1, that basically means that you have a very uniform structure. So you have all sorts of molecules with very similar weight, uniformly dispersed into the structure. Whereas if you have this much smaller than 0, then you will have a very non-uniform, right? Is it smaller than 0 or bigger? Or bigger? Okay, well, it's going to be bigger. Yeah, so this is one structure, one index that is very important, but that's going to give you, like, as I said, how uniform the weight is dispersed and stuff. But there are a lot more other properties, like mechanical, thermal properties that you have. So this is a table showing you some examples of, I don't think you have the PI index here, but I think there's another table in your textbook that gives you some examples. So this is showing you all sorts of examples like polyurethane, as opposed to, for instance, PMMA. If you look at their properties, so the water absorption, how much it can vary, but then you can have a look at the bulk modulus, so how much it basically, how stiff it is. You have like 2 gig, whereas for polyurethane you have like 0.8 or something like that, quite small. Tensile strength can vary a lot. This is elongation at break, so you can have something that is very flexible, like polyurethane. You can, this is basically like huge, 500%, you can just stretch it and it never breaks, it goes back to where it was, right? Whereas, keep going back to that page. PMMA, if you look at there, it's like just 2%, so this is very similar to even something like bone, basically. So you know how variable they can be. Like TG, we'll talk about these glass and melting temperature in coming slides as well. The other very important is, as I said, the mechanical properties. So for most of the polymers, we're talking about tensile properties. But obviously, for some of them, you would like to talk about the compressive properties as well. Depends on the type of them. So for the tensile properties or even compression, basically for mechanical properties, you're looking at the stress-strain curves usually, right? So just like normal materials. So you can have brittle, but you can have all the way that kind of behavior, which is very rubbery, or something in between, which is like a ductile material. So like, if you think about metals, this is a very similar concept. So, but again, for instance, for a very same type of polymer at different temperatures, at different rates of loading, you can have all sorts of spectrum of behavior. So you can have a rubbery, but then you can increase the strain rate all the way, and then it behaves very differently, right? Good. So this is a very nice thing about polymers, how different they can behave. And then, again, they are going to behave based on their structures. So, as I said, this is like a polymer. The concept is just a chain of molecules, right? Then, depending how this is, the structure is, sometimes you can have a very long chain of molecules that are just very long, and then they are amorphous. So they are like very messily, just around. So you can tell that this one, if you stretch it, it's not going to break, right? It's just opening up because the bonds, there's not much bond in this long chain. It's just like a rope that's been, pulled together. Now, if you pull it along, it's going to be very rubbery. That's why, so it doesn't resist much to compression. So when you're applying any load, there's not much resistance, as I said. You can just go along and then come back to where it was, right? Whereas sometimes you have maybe very similar material that you have in this chain, but then it can be very organized, which is what we call it crystalline or semi-crystalline. You have this in your textbook. More detail if you're interested. So if it's more like oriented, more organized, it's like crystalline material. Then it can be, the behavior can be just like a solid material. So you will have something like that. So for instance, examples of like polyurethane, so like rubber is very much like this, so you can just stretch it all the way along, but then PMMA, like polyethylene, I guess, is just something like that, right? So we have glossy or semi-crystalline polymers, as I said, or amorphous one. So even with the amorphous, you can have a concept of strain-induced crystallization. Basically, you can, so you have this, you can stretch it until it opens, and sometimes they start to orient in one direction and become more like crystalline. So you can change that property by at different temperatures, or by just the stretching it, because it's like more mechanical induced crystallization, if you like. And again, just like in other materials, as I said, we have ultimate stress. So you can pull them until they break. If they're rubbery, obviously, they're not going to break very soon, so they will have a very big ultimate strain, whereas maybe the ultimate stress is not as big. Whereas if you have a crystalline one, the ultimate stress might be pretty big. But then the other very important concept that we have for strain, for failure materials, is the toughness. So what we call toughness is the energy absorbed before it fails. You probably have had it before. Do you know what toughness is? You should know it from your solid mechanics and stuff. Before you read the note, obviously. So the toughness is, again, as I said, we're just working a lot with the stress strain curve. So you want to calculate, this is basically the energy, right? Energy is always force times by distance, right? That's work or energy. So again, in here, this is the energy, and for this material, that's the energy that the material absorbs, right, before it breaks. So, interestingly, it doesn't necessarily depend on the stiffness only, so you can have a very stiff material, and it can break here, whereas if you have a very soft material, and if I go on, if it breaks right here, therefore, you will have a much tougher material here compared to this. So it depends, whereas maybe opposite. Maybe it breaks right here, but if it's like very stiff, then you have again, a tougher material. So it's a combination of elasticity and the stiffness of the material altogether. Any questions from these? Is that clear? All good? So if I give you a material and I ask, give me all the properties based on the stress strain curve, you'll hopefully be able to do that. Okay. So yeah, that was just for a tensile stress. So these are more like quasi-static mechanical testing. So you just put the material in a mechanical testing machine and stretch it until it fails, and then you will have all the properties, right? But then we have another concept of fatigue loading, as you basically should know. So in fatigue loading, it's not just one time that you apply the load of quasi-static. It can be dynamic, so it can be very fast and it can go forever. So if you think of the heart valve that I showed you earlier, it's like your heart is never supposed to stop working. Basically means that it's working all the time. So it's applying that sort of load to the heart valve, the artificial heart valve, all the time. So you need to think about the fatigue properties of this material, because at a certain stress level, your material can last once, or maybe twice, or 10 times, but then you need to apply the stress such that it never fails, basically, right? So if you think about this SN curve, that's the maximum stress that you apply to a material, and then this is the number of cycles to failure. So if you're here at the maximum level, you can basically fail very quickly, whereas if you reduce the applied stress up to here, it's like sort of converging, so hopefully it will never fail. So this is very important when it comes to the design and the selecting of the materials. You need to know what sort of stresses you're applying to a material when you put it in the body. For instance, again, just like joints as well. So if you have an implant, that's again under a lot of fatigue loading. So there's a lot of cyclic loading when you're walking, running, or whatever. So you need to have an idea of what sort of stress level you're applying to the material, and then also what strengths, what fatigue properties that material has. So you need to measure that. The other very important thing about the polymers is the thermal properties. Just like any other materials, if you think of the simplest one, I guess, is that we learned the very first time at school was the water. So if you think of water, you can have solid and then gas and in between liquid at different temperatures, right? This is the same thing for polymers. So at different temperatures, they're going to have different properties for very different materials. If it's a semi-crystalline material that has already a structure, right? So it already has a structure. It's like at room temperature, if you think about it, semi-crystalline, it has a structure. So if you increase the temperature, there is a melting temperature. So it will start to lose the bonds and it will get like a liquid more. Whereas if it's a linear amorphous, if it's an amorphous material that there is no structure already, even if you increase the temperature at this level, there is no something as such like melting temperature, because it's not gonna, there's no change in that phase, if you like, right? It's already liquid, so you don't have any melting structure. But if you think about TG, which is the glassy temperature, all of the polymers have that. So either it's a semi-crystalline or it's a cross-link or a linear amorphous. Either there is a structure or there is not any structure in the polymer. If you decrease the temperature, it's going to even be more crystalline, so more organized, and then you will have a network of crystal that it becomes more like a solid material, right? So you can work on that. And obviously, different polymers by nature at room temperature will have their different behavior. So this is giving you just two examples. For instance, a squishy ball is just at room temperature, it's above its TG, so room temperature you will see that it's like a rubber, it's already beyond the TG, right? So it's not a crystal. Whereas if you decrease the temperature for that squishy ball, it's going to get a lot more solid. Whereas PMMA at room temperature has been used below its TG, so if you increase the temperature, it's going to like melt. So as we said, it depends on the structure. The higher your molecular weight is, and the greater you have chain cross-linking. So if you have your polymer, if you have more cross-links between the different chains, or if you have an oriented chain, you're going to have a higher melting temperature because it's just more organized. So you need to spend more energy, basically you give it more heat as an energy to just break those bonds and then make it into a liquid. Well, maybe you can call it liquid, but melting temperature. Questions? So there are ways that we can determine all these structures. For instance, for the molecular weight, we can use gel permeation chromatography. So these are just different devices that you put the specimen in, and then based on different concepts, they can measure the molecular weight. So this chromatography is just going to absorb different molecules with different weights at different levels. So then based on that, based on the color of the absorption, which is calibrated already, you can figure out what's the concentration of each weight, basically, and then you can figure out the molecular weight of the polymer. For determining the structure, you can use different devices as an infrared spectroscopy, nuclear magnetic resonance, wide-angle X-ray scattering or small angle X-ray scattering, and also electron microscopy. So with the electron microscopy, it's just a type of microscopy, so you definitely need to slice down the polymer. So basically, it's what we call a destructive testing. So if you don't care about the polymer, to use it afterwards, you can definitely use this. And also, you would require the molecules to be large enough for the microscope that you're using to be visible. Whereas the other ones, you can basically determine finer structures in the polymer, and also they are not necessarily destructive. For the mechanical and the thermal properties, we have a mechanical tensile test, as I said, so it's most of the time similar to standard mechanical testing machines, which you have definitely seen in your workshops and labs, right? So with that one, you just install a specimen into the machine and then apply a tensile test. There's another one, device called dynamic mechanical analyzer, I guess in this case. So this one is more like to measure the mechanical properties of the system. I'll talk about in the next slide, I think. The other one is surface characterization. So this is very important in biomaterials because basically initially what you make so the surface is also behaving similar to the bulk modulus. So the surface and inside of the material is basically the same material initially when you make it. But then the surface becomes very important, and we are very interested to the properties of the surface of the material that we put into the body. And the main reason is because it's in contact with the body, right? So it's very important that once you put it in there, what will happen? So does it absorb materials from your body, or does it, release some materials to the body? Most of the time, it's a problem because you don't want any particles from that material to, just move around freely in the body, in the blood, or you don't know what happens. So that's very important. And also, the other thing that we have, for instance, if you think of an implant, once you put it in the body, like for dental or even bone or anything, you would like it to be integrated with the body, right, with the existing tissue. So again, you want to think about the surface, which is, you don't want it to be too smooth. So if it's a little bit more porous, the integration will happen better. So with different applications, you really need to think about how that surface properties are. And I think in next lectures, we'll have more about this as well. So that's something to have in mind, especially for your project. You want to think about the properties of the surface of the material very well. Okay, so the dynamic mechanical analysis. What's happening here is that this is very similar just to a normal mechanical testing machine, where, so in these ones, the special thing is that you put the specimen in there, but then we talked about how polymers can behave differently in different strain rates and different temperatures, right? So you would like to measure that. What this device does is that it automatically applies a very different range of displacement to the material. Most of the time it can be from 1 hertz to 1,000 hertz. So it starts from very slow and then, vibrates in the wide range of frequency. And also the other thing that it does is that it slowly increases the temperature of the environment. So you can see that there's a chamber in here. So we put the specimen here, we close the chamber, and then it can increase the temperature, and then starts a slow displacement, and then, goes vibration. And what it does is it's like characterizing the entire property of the material, how it responds to that label. So this is an example of output of these machines for 2 types of polymers. You have a highly cross-linked, which is again like a more crystalline structure, versus a lightly cross-linked. So you don't have much links, across the polymers inside. So here you have increased the temperature, right? And then you have E prime and E double prime. Do you know what they are how do you determine that? Basically, these are 2 different elastic modulus of the properties of the material. How do you determine what is E prime, what is E double prime? Do you know that? If you think of a viscoelastic material. So, So the concept that we have in these basically viscoelastic materials, which polymers are most of the time very viscoelastic in a very narrow range of applications, is so you apply a displacement, right? And this is time. So what the machine does is that, okay, it applies different displacement at different frequencies, so it can change the frequency, all the way to very high frequency. What happens is that you measure the force, or if you like, the stress, right? If you just focus on this part, so you have a T0, for instance, and then 1, if you like. So when you apply the strain, right, the maximum strain is happening at this time, okay? But if you measure the stress, it's going to be like that, okay? But it doesn't necessarily, so your maximum stress, the maximum stress doesn't necessarily happen at the same time. There's a lag in there, right? So you will have a T0 prime, okay? And if I give you an example, just think of if you have a perfectly elastic material, just like a spring, right? So when you apply the stress, when you push it, at the same time, it can apply a stress, load back, right? And then if you release it, it goes back right on the spot. But if you think of a sponge, right? If you press it, then when you release the stress, it doesn't go back simultaneously, right? It takes a little bit of time for that to go back. So that's the term of viscoelasticity. So if you have a perfectly elastic material, this maximum stress, and also here, happens at the exact same time, so you don't have any phase lag, what we call it. Whereas if you have a if you have a perfectly viscous material, you will have a phase lag of 90 degrees, right? It takes a lot of time for that material to get back to where it was. So this is the concept of viscoelasticity that you have. So what you have also in your textbook is that if ideally you have a strain, I'm going to use the exact terms that you have in the textbook. So if you have a strain at a certain frequency that equals to a zero initial strain, and then it's like a sine wave, imagine, right? The response, which is the stress, can you see with this? The response, there is an initial or magnitude of the stress, whatever it is, right? But then you have at the same frequency plus a phase lag, right? So that's what's an indication of this time difference, basically. So if you have an elastic material, this delta equals to 0, whereas if you have a perfectly viscous material, this is going to be 90 degrees, okay? So this is giving you an indication of how viscoelastic your material at a certain frequency is. It can change. At very low frequencies, it can be very different what it is in very high frequencies, right? So this is a general concept. And then if I plot the stress strain, so this is a strain versus time, stress versus time, right? So if I put together the stress and the strain, it's going to look like this most of the time, okay? So this is when I'm applying the load, going up, right, all the way right here. And then this is when I'm coming back. So if you look at the fatigue properties or viscoelastic properties, most of the time it's like, you know, that sort of thing. So there's always like a hysteresis in there. So this is the stress strain curve. And then if I assume that this is like a linear, look at the slope of the loading curve, it's going to give me the E prime. Whereas if I look at the slope of the unloading curve, it's going to give me the E double prime. So that's the storage moduli. So the name comes from that you're storing that energy, right? So you're going up, the material is storing the energy. Whereas when you release it, it's giving back some energy. That's why we call it loss moduli. So the more, it depends basically how much of energy that you have put into the material is going to give you back, release it. That's where the name comes from. So you have two concepts of loss moduli and storage moduli that this DMA is going to give you. And then based on that, for different types of polymers, you will have different properties. So you see that in different range of temperature also, the properties, the behavior is very different. Okay. Any questions on that one? Okay, yeah, so that was just an overview of how it works. And then, again, this is just different applications coming back to PMMA, which is like more crystalline material, like contact lenses and bone cement, whereas all the way you have like nylon as sutures, which is, again, as I said, very... This is also viscoelastic, so when I release it, it takes time to come back. You see? That's actually viscoelastic because there are just joints in there. There's some friction in there, so it takes time to come back. Okay, and then, yeah, so this is just a summary how polymers are synthesized, basically how they're processed. That's what they call in chemical engineering. And then how they're behaving, so structural behavior, and then based on their covalent bondings and the chain structure arrangement, how they can behave, so they can have a variety of mechanical properties and variety of temperature properties, temperature-based properties. Yeah, so that's all you basically need to know about polymers at this level. It's not very detailed. There's a lot of chemical engineering background into it. So that as a chemical engineer, you probably would know a lot more about how polymers are basically made, how they are synthesized, and what's the main structure of each different polymer, and then what's the potential for different structures. But in this textbook, there's a good, like a summary of the structures that are available, and then if you want to think of a design for a specific application, you can find good information in there. Okay, any questions? If not, I'll see you on Friday. Oh, yeah. Find information on Wikipedia better, but... Hey. Did I put my email in there? So do you want my email? Email me and then send me your videos. So what exactly are you doing?
So you should always to do a mix of biomechanics and electronics. So yeah, process.
So we do like that.
So I've done medical electronics. And also I've done the biomechanics courses. I feel like I really like that.
Yeah. All right. Yeah, we can talk about it.
Can you describe it?
FMAL at university.edu.
Thank you.
Yeah, no worries.
I've been trying to talk to her about he's away.
Yeah, I think he'll be back next week.
It's 19th, but that's for...
I don't know, when was the deadline for you to... It was a deadline, right?
My scope is more later, but I think I need to ask the coach. I mentioned the topic. So else can I email? He's questions.
He's a coordinator, yeah. So what do you want to find out? I don't know, talk to these people in the class. Maybe ask if anybody hasn't found anything. Yeah, sorry. I think the best person is just Peter. Yeah, because I don't even have access to emails. Yeah.
I was wondering if you could please post the slides onto the LMS.
Yeah, sure. Yeah, I'll do it.
Thank you.
Yeah, sure. No worries.
I'm interested in any, I was really intrigued you were talking about the imaging stuff in terms of helping out. So I'd really like to get a feel of what, I don't know how to frame it. Is there's any opportunity for to help out a little bit to kind of see what really happens. So this is all good like learning a lecture environment, but until you actually get out and see what actually happens.
Yeah, I know.
Yeah.
Yeah, so what we're doing is, what I'm more involved in microcity imaging.
Yeah.
I do finite element stuff as well, so we use, again...
Definitely relevant to what we're doing now.
Yes, exactly, because you're using mimics and stuff, so yeah, we do some